Okay, in this video we are going to talk about moment of inertia. This is from chapter 7 of your book. So let's see if I can hide this guy from here. This guy, no. Alright, so we define moment of inertia as follows. So this chapter, moment of inertia, is completely a geometrical discussion, geometrical property. So we are gonna focus on second moment of inertia. You have become familiar with first moment of area, but second moment of inertia is something we're gonna talk today. So as I said, this is completely geometrical property, and it's a mathematical discussion. So completely mathematical. So if you look at an area like this, and then I define x-axis like this and y-axis like that, then moment of inertia of this area about x-axis is defined like this. So if I consider differential element like that, and then this differential element has coordinate x and y coordinates, right? So moment of inertia about x-axis is defined as y squared, y, I would say y tilde squared of dA. Okay, y squared dA. So what does that mean? It means that y coordinate of this differential element dA squared times dA. Then if we evaluate this integral for the entire region that I have here, it's going to give me second moment of inertia about x-axis. And then similarly, I can define Iy equal to x squared dA. So this is like a double integral you need to evaluate, right? So if you look at dA in Cartesian coordinate system, you have dx and dy. So you can write this integral like this, a double integral y squared dx dy, right, for that region A, right, this region A, and then same thing here. Okay, so this is a double integral, but I'm going to show you guys a way that we can, it's possible to avoid double integral when you want to find the moment of inertia about x and y axis. I'm going to show you guys how we could do this. All right. So as an example, let's look at an example. Let's see what would be moment of inertia of a rectangle about, let's say we have a rectangle, and then this is like my x-axis, and let's say the base is b, and this is height. So x and y, right? And then we want to see what's the moment of inertia of this rectangle about x-axis. How do I find it? All right, so to find this, you don't need to evaluate, do this, find Ix like using double integrals. If I consider my differential element like this, then this is like dA, right? So what would be, by the definition, what would be for this dA, what would be differential moment of inertia about x-axis for this shaded differential element I have? This shaded differential element you see here, let's say it has distance of y from the x-axis, right? So by definition, this shaded area has It has everything on that shaded, that the differential element has distance of y from x-axis, right? So by definition, I can define, I can find dix equal to y squared dA, right? Because uh, for that shaded area, you see shaded element, everything has same distance as y from x-axis. So dix, differential moment of inertia by the x-axis for this f differential element is going to be y squared dA. Moment of inertia, second moment of inertia, is kind of tells us how an area is distributed, how far the area is distributed around about an axis like x-axis, right? So the larger this moment of inertia, it's like your area is farther from the x-axis. All right, so this is differential moment of inertia for this differential element. Okay. If I want to find for the entire rectangle, I need to take integral of the left side for this rectangle, right? And then on the right side, I have dA. dA is what? Your width, b, and then if you call this dy, b dy. So integration of this guy, right? So how much y varies in this rectangle? It varies from 1, 0 to h. So you guys see, instead of doing dA as dx dy, by making a differential element like this, I ended up with just single variable integral. Makes the life easy, right? Okay, so how do I take this integral? On the left side, if you consider all differential elements all the way from the bottom to the top, find their moment of inertia, add them up. On the left side, you're going to have total moment of inertia of the rectangle about the x-axis, right? And then on the right side, this guy, b's constant, comes out, and then y, if you find moment of inertia of that, integration of that, it's going to be y cubed divided by 3, going from 0 to h. So if you put values there, this is what I'm going to find. b divided by 3, h cubed minus 0 cubed. So this is what we found. Moment of inertia of a rectangle about its base, x-axis passing its base, is going to be b h cubed divided by 3, right? So this is what we found. Alright, so what happens if I'm interested in finding moment of inertia about y-axis for this rectangle? Do I need to do this integral again? Not really, because what we derived here, here our base was in agreement with my x-axis, that I took moment of inertia about that, and then the formula came out like b h cubed divided by 3. So if I want to do it about y, the only thing changes is this. I have to switch b and h, right? So moment of inertia about y-axis is going to be h b cubed divided by 3. Same thing, right? Similar formula. Alright, so that was important, right? So now let's see what happens if I'm interested in finding moment of inertia of a rectangle about an axis passing its center, like this, right? This time, now it's b here, this is h over 2, this is h over 2, entire height is h. So what happens now? What is moment of inertia this time about x-axis? Alright, so here, you can think of this to be made of two rectangles, right? One here, one here. And for this top rectangle, what is moment of inertia? We just found a formula, right? So if I say Ix, total Ix is gonna be, if I consider this first part, and the second part, since the moment of inertia is basically integration, if you break, so for Ix I have to do this integral, right, for the entire area, right? Since it's like integration, instead of doing this integral for the entire thing, I can take the integral once for region 1 and then do that the same thing for region 2, right, and then add them up. So for first one, this I just found the formula. So if you have moment of inertia about x-axis passing the base of the rectangle, for this rectangle it's going to be what? It's going to be b, and height cubed, height is h over divided by 3, and then plus, okay, something else you guys notice here is that look at the formula for a moment of inertia. So this is y squared. Y is the distance of a differential element squared. So if you have the differential element here, this is your y, right? If you have differential element at the bottom, your y is going to be what? Negative y. But in this integral it doesn't matter, because we are going to square y and y squared. So for this bottom one, we can still use this formula, right? Because it doesn't matter, you are under the x-axis, you are above x-axis, moment of inertia doesn't matter, right? As long as the distribution is same way. Okay, so for this bottom one, moment of inertia is going to be the same thing, bh over half cubed divided by 3. So let's see what we get here. So bh cubed, 2 cubed will be 8, 8 times 3, 24. Same thing here. So I get what? I get bh cubed divided by 12. That is interesting, right? Because what I found is moment of inertia, right? Moment of inertia. Okay, let's summarize what we found. For this rectangle, about x-axis, right, when this is base, this is height, Ix was bh cubed divided by 3. And then for this one, when x-axis passing this case, right, this is h, Ix this time was bh cubed divided by 12. And that makes sense, because you see this one is smaller than this one, like 1/4 of this one. But this makes sense to us. Why? Because if you compare this case with this case, in general the area here is distributed closer to the x-axis compared to I'm sorry, it's farther from x-axis compared to this case. You see, at most here your areas are at most like h over 2 away from, apart from x, and here negative h over 2, right? So in general they're closer than this case. So that's why here Ix is smaller than this one. Make sense? So that makes sense. As I said earlier, moment of inertia is basically a measure for that tells us how far, how distribution, how our area is distributed about the axis you are interested in. Alright, so okay, just hold on, let me check everything, make sure that everything is being recorded. Alright, so let me open it up. Alright, so so far I defined moment of inertia, and so we define moment of inertia. So let me grab this guy, bring it down. Okay, so define so far moment of inertia, and then I told you that I found the formula for um, rectangular section, right? Rectangular area, the formulas we found. This formula is going to be very useful for us when it comes to finding moment of inertia for other shapes. Okay, so next let's look at this problem, this example. Let's say I have this is my area, this y-axis, x-axis, this is length is a, this length is b, and then the function that describes this curve is kx this, right? So what you want to do is this. The problem statement says what is ix, right? So we want to find moment of inertia of this shaded area about x-axis. That's our problem. First of all, before I move on, I want to show you a relationship between a and b. So in this function, when x is equal a, y is b. So k in terms of a and b is going to be this, b divided by a, this, right? So let's keep this in mind. It's going to help us later. Okay, so I want to find moment of inertia about x-axis. So let's take differential element like this. You know, again, by definition, we go back always to definition, right? If you consider a differential element like this, then differential element, like by definition, like this dA, right? And then this is y distance of it from x-axis. Integration of y squared dA is going to give me moment of inertia about x-axis, right? But here, by taking my differential element like this, I'm going to make the integration a bit easier, right? For this differential element, this is like a rectangle. This is a narrow rectangle, differential rectangle, right? Differential element. What is this length? Is dx. What is this height? Is going to be y, right? So here actually what I have here is what is my, for my differential element dA is what? Y dx. So you see what type of differential element I'm using. By doing this, I'm going to avoid taking double integral. Alright, so technically by definition you have to take double integral, but by this trick that I'm using, you can do all problems without taking double integral. Alright, so okay, so look at this dix. For that differential element, what is moment of inertia about x-axis? I just proved that to you, that if you look at a rectangle, moment of inertia about x-axis is going to be base height cubed divided by 3. So I can apply that to this differential element too. For that differential element, what is the dix? Is 1/3 of your base is dx, your height is y, right, cubed divided by 3. Then ix is going to be what? Integration of y cubed dx divided by 3. I need to evaluate this integral. Okay, so this integral, the range is important. Range of x is what? From 0 to a. My y is cubed. So look at our function here, y is cubed. So if I cube y, on the other side I'm going to have what? K. Okay, let me write it. Right? This is what I get, dx. And then this is going to be equal to 1/3 of 0 to a, k cubed times x dx. Alright, so k cubed is a constant, I take it out. I'm gonna have what? 0 to a x dx. What is integration of that? K cubed divided by 3, x squared divided by 2 from 0 to a. So this is what I'm gonna get. My integral is gonna give me this 1/6 of k cubed divided times a to squared. Alright, we can simplify this further. Look at here, k is this, so if I want to find k cubed, it's going to be b cubed divided by a. So let's put it here. Now my answer will get simplified a little bit. So k cubed is b cubed divided by a, and then a squared, and then I'm going to get 1/6 of b cubed a. This is what I found. This is moment of inertia of this shaded shape about x-axis. Right, so this is moment of inertia about the x-axis. Alright, so what if I'm interested in moment of inertia of this shaded area about y-axis? This, what we did here, is called moment of inertia by integration. So the question now is, what would be moment of inertia about y-axis? Let's do that. For that, I can still use the same differential element I had. So let's see. Still have my differential element like this. It has length dx, this is y, this is a, this is b. This function is k, this, right? Okay, so this time, what would be diy, moment of inertia of this differential element about y-axis? If you look at this area now, all of it is the same distance from y-axis, right? Everything here is. So what would be by definition moment of inertia of this narrow differential rectangle I have about y-axis? It's gonna be whatever the area is times its distance squared, right? So then what was dA? dA is y dx. This is the right dy, and then take integral of both sides. Get what? X squared y dx. X goes from 0 to a. Alright, so now we have to evaluate that integral. So what was x? I leave it as is. Y is what? Is k x to this power, and then dx. Alright, so I take the k out. I'm gonna have what's remaining in the inside will be 2 plus 1/3 of dx, and then will be what? X 6 plus 1, so 7 3 dx, and then okay, what is integration of this guy? Is easy, right? This will be 7 over 3 plus 1 divided by 7 over 3 plus 1, right? And range from this to this. So this is going to give me k a to this power. 7 over 3 plus 1 is going to give me a to 10 over 3, the power, and then here 10 over 3. Let's simplify it. Set 3 over 10, k a 10 over 3. So what is k? Again, go back. We had k equal to right? So if put here this, then 310 VA. Okay, if you simplify this, will be 10 over 3 minus 1 over 3. Then I get 310 of VA cubed. This is IY. Alright, so IY was 3/10 of VA cubed. Alright, this is how the method of integration works. So if you want to do moment of inertia about x-axis, you see I took the differential element like this, and I said dix is this, and then I took the integral. And then for if you want to take moment of inertia about y-axis, same element, but this time diy, remember, is going to be x squared dA, and like this, you take this integral. By this method I just showed you, you can do any moment of inertia by integration for any like arbitrary shape. Sometimes you may have like something like this, like, you know, trapped areas like this. What is moment of inertia of this guy? You know, let's say this is like curve y2, this is curve y1. What is moment of inertia of this shaded area about x-axis? How do I do that? You know what? You can think of this to be equal to, you can think of this problem to be two problems. Solve this problem 2 times. Once you just consider this shaded area with y2, and then you consider another case, shaded area with this case, right? This is y1 function, this is y2. So if I find one moment of inertia for this one, I'll call it I2, I call this one I1, I can simply subtract these guys from each other, I1 from I2, and then that's going to give me what? Ix of the shaded area about x axis. Make sense? Why we can subtract this? The reason is because moment of inertia, as I said earlier, is just integration, and for integration we can do these operations, right? So if you have more complex problems like this, when you have trapped areas, you want to find moment of inertia, this is the way you guys can do, right? Okay. Okay, next thing I'm going to talk about is, if you hold on, let me again double check everything is going well. Yeah, we have 30 minutes so far. Okay. Next thing I'm going to talk about is polar moment of inertia. So far what we did was we had moment of inertia about one axis, right? But polar moment of inertia is defined like this. Polar moment of inertia. So how we define it? Like, again, this is a mathematical thing. If this is like your area, and this is like x-axis, okay. You guys learned that for x-axis, right? We define Ix equal to y squared dA. For Iy, we define it x squared dA. But now I'm going to define polar moment of inertia like this. For polar moment of inertia, what matters is it's moment about a point, it's not about an axis. So let's say we have point O, and then I define this distance from the differential element to the origin, this point rho. If I define that distance rho, polar moment of inertia Jo is defined like this: rho squared dA. So if you evaluate this integral, rho squared dA, you're gonna find moment of inertia about 0.0. Makes sense? So this time, this is moment of inertia about a point. So this is a measure similarly. This is a measure that tells me how your area is distributed about a point instead of axis. Alright, but look, if you look at this triangle, right triangle, this is like a right triangle, right? So I can write Pythagorean theorem like this. In this right triangle, you know that rho squared is gonna be x squared plus y squared, right? So if this is x, this is y, then rho squared will be x squared plus y squared. Alright, so then polar moment of inertia, let's look at it. It's gonna be equal to, right? It's gonna be equal to x squared plus y squared dA, and I can distribute dA into here, so it's gonna be like this: x dA plus y squared dA, right? And then integral like this, you can break it like it, right? If this guy is a continuous, right, area, you can write this. So what is this? This is actually I y, and this one is I x. So what I just showed you is this, that polar moment of inertia. So if you have this, right, you are looking at point O. Polar moment of inertia about O equals, if you have defined your x-axis like that, y-axis like this, polar moment of inertia about O is going to be equal to second moment of inertia about x plus second moment of inertia about y. So Ix plus Iy. Make sense? So I just proved that to you. For some problems, finding polar moment of inertia is going to be easier. For example, for circular cross sections, right, it's always easier to do polar moment of inertia. So let's do an example here. Let's say I have a circle, and then I want to know what is polar moment of inertia of a circle about point O. Right? How do I do that? Okay, so again, technically this is polar moment of inertia, right? This again, if you consider like differential element, could be like a double integral. You know, that may result in double integral. But I'm gonna show you guys that how we can avoid this and just take this using single integral. For a circular cross section, if I consider the point O, so if you consider my differential element like this, like a ring, that ring, right, that's like a narrow ring, and then for this ring I'm gonna have area, right, dA, and then the distance of this ring from the point O is, if I call it rho, right? So for this ring, everything, so differential polar moment of inertia about O is equal to what? For this ring, since everything is located at same distance rho from it, it's going to be basically dJO is going to be equal to rho squared times dA, right? Okay, so for this dA, what is the area of this ring? If I unwrap this ring, it's gonna be like a rectangle, right? So what's gonna be the length? It's gonna be 2 pi circumference or perimeter of the ring. And then what is the height? It's gonna be d rho. This differential element, so is rho, and then the thickness of it, the width of it, is like d rho. Alright, so what is dA? dA is gonna be 2 pi rho d rho. So this is differential polar momentum inertia of this element about O. Okay. But in order to find the JO, I need to evaluate this integral, the entire thing. Rho going from 0 to R. R being the radius of the circular section. So here's the integral I have to take. So you take 2 pi out because it's constant, and then you get what? Rho cubed d rho. And then what is this? Rho to the 4 divided by 4, going from 0 to R, and then I'm going to get this pi radius to the 4 divided by 2 is your polar momentum inertia about O, right? About point O. Okay, so this is what I found. Alright, so now let's say I'm interested in finding the second moment of inertia about x-axis and y-axis for a circle, right? Okay, so so this is JO, polar moment of inertia for this, but we know on the other hand that JO is equal to IX plus IY, right? So if you look at a circle is symmetric, right? So if you take moment of inertia about x-axis or y-axis, they're going to be the same because it's symmetric, right? And x is like axis symmetry, same thing here. So IX and IY are going to be equal for a circle. IX and IY are equal. So IX or IY, right, are going to be equal to half of polar momentum inertia, right? So IX and IY for a circular cross section is going to be 1/4 of pi radius to the 4th. Alright, so this is a good useful formula we found. So you know, with this trick I avoided doing an integration for IX or IY. You could do it this way, you know, you could just take differential elements like this, you know, and then find the moment of inertia about x-axis for this quarter circle, right? And then we multiply it by 4 because this, they are distributed about the x-axis like same way, right? So moment of inertia is this are equal. So if you find for 1, multiply it by 4, you have it. Alright, so but with this trick I avoid it. Now that I have polar moment of inertia, I don't need to find those. Alright, so let me stop the lecture here, and then the second part I'm gonna continue talking about moment of inertia in the second part. Let's have a short break and we come back.